Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. So we all know what the square root of 9 is, but do we know what the square root of 9.1 is? Unless you're a human calculator, you probably don't know that off the top of your head. In the era before calculators and phones, mathematicians needed a way to estimate complex values using only simple arithmetic. This is the core of linear approximation. The big idea is this. If you zoom in far enough on any smooth curve, it starts to look like a straight line. And if we know the equation of that line, the tangent line, we can use it to predict values of the curve that are otherwise impossible to calculate by hand. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So let's take a look at what linear approximation is, and then we're going to draw a diagram to illustrate what exactly is happening. The linear function L of x, which is equal to this expression here, is called the linearization of f at a. And for x close to a, we have f of x is approximately equal to L of x. And this approximation is called the linear approximation of f at a. Now let's draw a diagram so that you can see what is actually happening. So let's say we have some smooth curve f, and we're going to zoom in on it. So let's say once we zoom in, it looks something like this. So there's still a little bit of a curve. And now let's say our a value is right over here. Then that means our f of a is right over here. So then what we're going to do is we're going to draw the tangent line to the point here. So let's say our tangent line looks something like this. Now x is a number that is close to a. And what we want to do is we want to approximate what f of x is. So f of x is right over here. This is our f of x. But let's say that f of x is very difficult for us to calculate. So what we're going to do is we're going to use linear approximation. We know that the slope of the tangent line is f prime of a. And if we multiply that by x minus a, which is the change in x value from x to a, so this here would be x minus a. And if we multiply that by the slope, then we're going to get is the change in y value. So this change in y value here is f prime of a times x minus a. So now if we add that to our f of a, we get this value here, which is L of x. So that is going to be somewhere over here. And this is why it's important for us to only use linear approximation for x that is close to a. Because if our x is far from a, so let's say our x is all the way over here, then we can see that L of x and f of x are actually quite different. So one is here and one is all the way up there. But for x close to a, so let's say around this area, we can see that L of x and f of x are pretty close together. Next, let's take a look at how we can actually use this through an example. Here, we want to use linear approximation to estimate the value of the square root of 16.2. We're going to start by writing down our function f of x. So here, our function f of x is equal to the square root of x. Our x value here is 16.2 because we're trying to estimate the square root of this particular x value. Now, the a value is going to be something that is close to this x value and something that we can take the square root of easily. And in this case, our a value is going to be 16. And we know that f of a is equal to 4. Next, we're going to find the derivative of our function f. So f prime of x is equal to 1/2 times x to the power of negative 1/2. Or in other words, this is 1 over 2 times the square root of x. So to use the linear approximation, we also need to know what f prime of a is. So f prime of 16, and that is going to be equal to 1 over 2 times the square root of 16. So this is going to be equal to 1 over 8. And now we have everything we need to substitute into that equation. So we have f of our x value, which is 16.2. This is going to be roughly equal to L of 16.2, which is equal to f of our a value, so f of 16, plus f prime of 16 times our x value, which is 16.2, minus our a value. Now substituting in all the values that we know, we have f of 16 is equal to 4 plus f prime of 16, which is 1 over 8, times 0.2. And this works out to be 4.025. So therefore, using linear approximation, we have the square root of 16.2 is roughly equal to 4.025. Now, the second part of this question is asking us if this value is an overestimate or an underestimate. And to know that, we need to know what the shape of our function f of x looks like. So we're going to draw that on the side. We know that the square root of x is going to look something like this. So if 16 is right over here, and then we draw our tangent line to this point here, then that means the tangent line is going to look something like this. So this shows us that the tangent line is going to lie above the curve, which means our linear approximation here is going to be an overestimate. And if you actually put the square root of 16.2 into your calculator, you're going to get that this is roughly equal to 4.024922. Now for our second example, we're going to take a look at how to approximate the cosine of 62 degrees. So we're going to start the same way. We're going to write down our function f of x. So our function here is equal to cosine of x. Next, we're going to find the derivative of our function, so f prime of x, and that is equal to negative sine x. Now the tricky part here is writing down the a value. The closest angle to 62 degrees that we can take the cosine of and know the exact value is 60 degrees. However, in calculus, all the trig derivatives assume that we're working with radians, not degrees, which means we need to write down our angle in radians. And 60 degrees is pi over 3 radians. So our a is going to be pi over 3. This means f prime of a is going to be equal to negative sine of pi over 3, which is equal to negative root 3 over 2. And finally, our x minus a is going to be equal to 2 degrees in radians. So this is going to be 2 degrees times pi over 180 degrees, which means we have pi over 90. And now let's go ahead and put everything together. So we have L of x is equal to f of a plus f prime of a times x minus a. Substituting in the values that we have, we get f of a, which is cosine of pi over 3, which is 1/2, plus f prime of a, which is negative root 3 over 2, times x minus a, which is pi over 90. So this works out to be roughly 0.4697. And this is what cosine of 62 degrees is roughly equal to using linear approximation. And now let's do a quick recap of what we covered in this video. We learned that the big idea behind linear approximation is that any differentiable curve is going to look like a line if you zoom in far enough. And the center, which is our a value, is always going to be a value that we can compute the function of and the derivative of without a calculator. We learned that the linear approximation can under or overestimate the original function, and it's determined by whether the tangent line is above or below our function. And finally, we learned that proximity is of the utmost importance when it comes to linear approximation. And this is because linearization is a local tool. The further x is from a, the less reliable the result. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful,
Remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.